Hello, guys. Welcome to the next installment of the Extension to Trigonometry series. So today we're going to do some trig, which I think if you were to sort of do a sort of unbiased assessment of the 4-unit syllabus of integration, it's probably one of the hardest parts, to be honest. Yes, you learn new things like by parts and partial fractions, etc. But the trig part is quite difficult. So today I want to show you two things. One is the T results substitution that you use, which you learned back in extension 1 when you used to solve equations, etc., with trig. And the other one is basically to use to do one of my favorite questions, probably of the whole topic, and that's sec theta. So I want to show you a neat little trick that I'm going to do, and yeah, we'll see how it goes. So let's start with the T results. So integration with trig. So can I just reiterate how awesome this integration topic is? It's so diverse, and in extension 2, the rules are gone, right? There's no guidance, there's no leading you into a question. Well, sometimes there is, but rarely do you get it. So a lot of times you just get a question, and it's up to you to determine what technique you want to apply. And that's what makes this topic hard for some people, but super awesome for some others, right? Where once you sort of develop all the techniques and know when to apply them, this topic is amazing. So I guess if you sort of look at the textbook and just learn the techniques that they learn the questions and the techniques that they teach there, I'd say you'd be able to cover 75% of all questions. The other 25% is random, right? And it takes a bit of practice. Sometimes it's a combination of techniques, as you'll see later today. Sometimes it's like neat little tricks. So for the sec theta question, which I'll do towards the end of this session, it's one of those where you ask yourself the question, once I show you the trick, you ask yourself the question, so how would you know to do that? Well, to be honest, not all of you will. And that's the point, that in this topic, there are textbook ways of doing things, but then there are neat little tricks that come left field. So it's only through videos like this and just learning lessons with your teachers and tutors that you get that exposure. So that's enough about me rambling. I'm going to start with T results, right? So this is a very important part. This is part, in terms of, is it a textbook piece of theory, or is it like a neat little trick? It's part of the textbook. So in that it's quite a core part of integration. So where this comes about is you're going to be integrating expressions with trig, which unless you use T results, you really don't have a good way forward. So let's recall T results, where T results in 3-unit or extension 1 maths basically said, if I substitute T to be the half angle of tan, right, that opens up a number of things. So without sort of re-deriving the formulae, I'm just going to give it to you. Basically, if I have the half angle of tan equal to T, then the full angle of sine equals to 2T, 1 plus T squared, cos 1 minus T squared, 1 plus T squared, and tan full theta is 2T, 1 minus T squared, right? So that is given. Yeah? So that is given. I'm doing my highlighting boxes all opposite today, so maybe I'll put a box in pen and then maybe highlight inside. Yep. So with this in mind, we're gonna basically explore, so what happens when I use this expression for integration? So what that means is it's almost like substitution, but using this substitution as my starting point. So what I'm going to do also then, if that's the case, I'm going to need to find an expression for the derivative of this. So what I'm going to do, if I differentiated this guy, dt on d theta, right? Differentiate with respect to theta. I know when I differentiate tan, I get sec squared. And then the derivative of the inside comes up front, so that's like a half there. Now, I'm going to try to re-express this side here, the right-hand side, in terms of t. So I know this guy becomes a half. Now, sec squared using the identity is 10 squared. Maybe I'll go 1 plus 10 squared. 10 squared theta on 2. And you can see that 10 squared theta on 2, that's t. So this becomes half 1 plus t squared. Now, what am I trying to do? I'm trying to make d theta the subject. So therefore, d theta, oops, d theta equals 2. So d theta equals to 2, 1 plus t squared dt. And guys, this is the second and more, sorry, the second box I'm going to highlight, apart from the one over here. This one here is important. Basically, when I use my t result substitution, I'm going to replace anything that I can see with the full angle with this box over here, up here. And then I'm going to replace the d theta or the dx with this second box down here in the black. So I guess by combining the two, we can use t results as a substitution technique to try to bowl over certain questions. So if you copy that down, let's do a few questions, right? Copy that down, let's do a few questions. So I'll do relatively straightforward one first. So check this out, right? And I want you to see, right? If your teacher doesn't use the word technique, or they just teach you questions individually, that's not good enough in 4 unit maths. Because when you do 4 unit maths, I think it's more efficient to learn patterns and techniques for questions. So if I said to you, find using the substitution t equals to 10, instead of theta, maybe I'll use x, right? So if I said integrate, now 1 over 1 plus sine x dx. So if you look at that question there, you really can't do anything with 1 plus sine x. You're kind of stuck, because if it was just sine x, maybe you can sort of flip it and try to use the trig integration rules to try to do it. But when it's 1 plus, you're kind of stuck. So so I say to my students, whenever there's no squares, because if it's like 1 plus sine squared, maybe you can use some trig identities. If you can't use any trig identities, t results will smash it. So we're going to use this substitution and do two things. We're going to replace the sine with because that's full angle, right? I'm going to replace that with in terms of t, and I'm also going to replace this guy in terms of t. So I know, right? If this is the case here, immediately I know that dx or d theta I had last time was 2 on 1 plus t squared dt, right? I'm going to sub that into dx, and then I'm going to sub the full strength of sine with its t result substitution. So in other words, I'm going to try to transform this expression into an integral question with t as a variable. So 2t 1 plus t squared multiply. So that is that sine x there, and this guy over here. So it looks a bit nasty, and that's absolutely fine. It'll clean up nicely, I believe. And just to be clear, that dx there is this guy, right? Now, whenever you do this, I think a majority of the questions, when you common denominator at the bottom, it's going to cancel out with the 1 plus t squared and get you to a nicer place. So let's do that. So right now, let's focus on common denominatoring, if that's an expression. That, let's see where that takes us, right? So I'm going to leave this right side here untouched. So if I common denominator 1 plus t squared plus 2t, ooh, that's nice. Perfect square. Great. And guys, are you okay with me doing this? Right, because if I flip that on top, it sort of cancels out anyway. So I get an expression that looks like this, right? 2 on top of, that's a perfect square. So factorize that. dt. Look at that, right? Now I can integrate an expression with t, right? So if I take out the 2 there, put this guy back up just to make my life a little bit easier, right? That's linear. So derivative of the inside is 1, so I don't need that. So I can use 2, add 1 to that power, divide by that new power. plus c. Technically, I need to times up and by 1, right? It doesn't matter. That's my answer. So my answer here is, well, actually, be careful here. So the negative comes down, the negative comes in front. So negative 1 on 2t plus 1 plus c. Now, you got to be really careful here, right? Because if you wrote that as your final answer, you might lose half a mark because it's still in terms of t. The question was in terms of x. So all I got to do now is plug this guy back into the value of t, right? Yeah. So let's do that. So let me just undo that, get rid of that. Graffiti. All right, let's see. So my final answer is going to be negative 1 on 2 tan x on 2 plus 1 plus c, which is my final answer. Yeah, which is my final answer. Oh, actually, how come the 2 came downstairs here? The 2 is supposed to stay upstairs, so my apologies there. Let me rectify that. Right, the 2 is upstairs, right? It doesn't come downstairs. Yeah, so I don't actually need this guy here. Perfect. Is that okay? So that's how you use t results. Let's do one more, right? So that's my answer. Let me just give that a little bit of a neat highlight. Yeah, let's do one more. Oh, can't wait to show you my favorite question. Sorry, bear with me. Let me see if I can find you a good one. Let me see if I can find you a good one. Okay. Let's do this one. This is a classic as well. So looks very similar. So part B, you integrate 1 plus sine plus cos dx, right? So it looks very similar. We do it in a very similar fashion where we do almost a double substitution, right? Anytime you see the full strength angles of sine and cos in this case, substitute the t results into there. Every time you see the dx, use that substitution with the 2 on 1 plus t squared dt in there. So let's replace 1, 2, 3 with our t results, right? Including the differentiation there. So I'm just going to zoom in so I can be a bit neater. So that becomes 1 on. Now I know sine is 2t 1 plus t squared. This guy here is 1 minus t squared, 1 plus t squared, multiplied by 2 on 1 plus t squared dt. Right, so you can see if I common denominator that once again, right, this part down here, if I common denominator that, it'll be 1 plus t squared in the bottom, which nicely cancels out with that, and then I will try to clean up the rest. So let's see, I'll leave the 2 over there for now, 1 plus t squared plus 2t plus 1 minus t squared. I'm hoping that things cancel out there. 1 plus t squared multiplied by 2 on 1 plus t squared dt. All right, hopefully once again, you're cool with me doing this. Now let's see, cleaning up the bottom, what do we have there? We got, so 2 on top goes 2 times 1, yep. I got t squared's gone, and there's 2 plus 2t, so I'm just going to factorize this. Oh, look at that, that's nice, all right? That is nice, because then the 2's cancel out. I hope you're cool with that. Guys, integrating 1 on t plus 1, that's ln t plus 1 plus c. And once again, don't lose your half mark. Substitute the t value back in, which is ln tan x on 2 plus 1 plus c. Look at that. That's the technique. Now, are there harder questions for this? Absolutely. Is the process the same? Absolutely. Right? Try to replace all your full strength angles with the t result that you've derived from extension 1, actually. Replace a dx with this guy over here, and you'll be sweet, right? Sometimes the maths behind it leads you into a different 4-unit technique like partial fractions, by parts, etc. But overall, that's the approach. So hopefully that's good. Now, gives me an opportunity to show you my favorite question, which there's two methods to do it. There's a long method, which is using partial fractions. Oh, sorry, using t results. And then there's a hack, which does it in like 2 or 3 steps. So check this out. My fave, right? My fave in the whole integration topic. So example, find integral of sec x dx, right? This is amazing, guys. This is amazing. If there's one question to showcase, technique, this would be it, because there's a nice little hack behind it. So I'm going to show you what I'm going to call method 1. Yeah. So using t results. All right, let's go. So let me do this. So once again, can you see for this question, right? If it's sec, it'll be 1 on cos. It really isn't any identity that you can use. I can just, don't be confused, right? I can't integrate sec. I can integrate sec squared, that's 10. I can integrate sec times 10, that's sec. I can't integrate sec using any formulae or 2 or 3 unit technique, right? So this is how I'm going to play it. I'm going to, I know that this is going to be 1 on cos. So I'm going to say let x, or sorry, t rather, equal to 10 x on 2, right? Because the moment you let this happen, remember, I know that dx equals to 2, 1 plus t squared dt, right? Yeah. So therefore, using t results, I know that the integral of sec x dx is equal to 1 on cos, so 1 on, now cos, as t results is 1 minus t squared, 1 plus t squared, right? Multiply that by dx replaced with 1 on t squared dt. Now, this is one of those questions where it doesn't cancel out, because if you think about, or does it, sorry? Yeah, no, absolutely does, sorry. My bad. It cancels out, but this is one of those questions where the answer that you get once you cross it out isn't that simple, right? Because it leads you to another 4-unit technique. So I'm just going to put a 2 there, 1 minus t squared. Now, I'm just going to quickly pause here for a second. I'm going to ask you this question. What technique do you think I'm going to use now when there's 1 minus t squared on the bottom, right? That's the question. So if your training is on key, right? You would basically say, I can factorize the bottom using difference of 2 squares. If I can factorize partial fractions. Yep, that is the goal. So if you did it as 2, 1 plus t, 1 minus t, you should be able to smash that with partial fractions. Yeah. Now, let's quickly smash this to the side, where let 2, 1, 1 plus t, 1 minus t equals to partial fractions for a, 1 plus t, plus b, 1 minus t, right? If I common denominator that and get rid of the denominator to compare the numerator, I get 1 minus t plus b, 1 plus t. And then if I sub in when t equals to 1 to eliminate this guy, I got 2 equals to 2b, therefore b is 1. When t equals to -1 to eliminate the second bracket, I got 2 equals to -2a, therefore a is -1. Right, so what that means is this guy gets decomposed where a is negative and b, maybe I'll put the b first, so it'll be 1 on 1 minus t, and then a is -1, so 1 plus that. Yep, that's nice. So let me just make sure that's right. Did I do that right? Let's see. A is -1, b, so if I cross plus, so I'm just making sure that my mass is right. 1 minus t. I think I've got my negatives in the wrong place. Let me just see. T is 1, b is 1. Negative. Sorry guys, I'm just having a gander. Yeah, I think that's fine. Let me just make sure -1, sub 1 in, that's gone. That's 2, so b is 1, yep. When I sub minus 1 into here, oh no, it's minus 1, so it's positive. Careful there. Yeah, good thing I checked, right? Good thing I checked. So that's positive 1. That's a plus, perfect. Okay. So you know what? In that case, if they're both positive, I'm just going to swap this around. I like it when the plus 1 comes first, right? All right, let's do this. So that's ln. That is negative. Just be careful here, right? Because that's negative, I need a negative 1 in front, right? Yeah, it's almost like I need a negative up here, right, to make it work. So just be careful there that this becomes negative ln 1 minus t plus c, right? Now, feels like you're almost there, but you just got to keep going because this becomes ln 1 plus t, 1 minus t plus c. Now, remember, I can't have that as my final answer because my answer needs to be in terms of x. I'm just going to move this up because I need to have one more line in here, right, where it becomes ln 1 plus 10 x on 2 over 1 minus 10 x on 2 plus c, right, as my, in this case, my final answer. Yeah, now that took quite a while, right? It wasn't a short question, probably took about 5 to 7 minutes, something like that. Copy that down for method 1. Yeah, I'm going to show you, but before I do method 2, can I clean this up as an expression to this, because then I'll compare it to the hack, which adds it as a different solution. So for this one here, actually, I'll take a step back. I'll go back here. Yeah, if I kept going here and I said to myself, that is, sorry, let me zoom in. Right, I'll zoom in by doing this. So this one here was ln 1 plus t on 1 minus t, right? I'm gonna simplify this by going minus 1 plus t, 1 plus t. Yeah, just bear with me. Yeah, humor me. Let's take it down this route, right? So again, that becomes ln. Yeah, on top here is perfect square, so 1 plus 2t plus t squared on, and the bottom there is 1 minus t squared, right? Now humor me, because I'm going to split this fraction on top, where I'm going to say, I'm going to go 1 plus t squared. Yeah, separate to the 2t. Check this out. I mean, does that look familiar in t results? 1 plus t, isn't that the reciprocal of 1 minus t squared, 1 plus t squared, which is cos? So if that's a reciprocal of cos, I know this is ln of sec x plus, and isn't that 2t on 1 minus, isn't that 10? Yeah, that is a much nicer answer than the one downstairs. Yeah. So you either get the blue one down there into where there's like tan x on 2s, or you get this guy. Now, remember this answer, ln sec x plus tan x, because in method 2, I'm going to arrive there in like 2 awesome steps. Yeah. So recall that. Let's go method 2. Check this out. This is amazing, right? This is amazing. Yeah, I don't know whether this is in textbooks. I hope it is. I'm sure it is. But certainly I hope you teach it at school. So method 2. The hack, right? I don't have a good name for it. The hack is what I'm going to use. So we're trying to integrate, draw this a bit bigger, sec x. Now, dx. This is what I'm going to do first. Do you guys recall that if I integrate any function that's a fraction where the derivative is on top, then this is ln, isn't it? Yep. So check this out. You're not allowed to ask me why, because it just works, right? In what I'm going to do next. That's the rule I'm going to access, right? I'll leave it over here. That's the rule I'm going to access. You're not allowed to ask me why, because I can't tell you. What I'm going to do, step 1, let's put the dx over here, wider. Step 2, I'm going to multiply top and bottom by the same thing, yeah, and that's sec x plus tan x. Sec x plus tan x. Guys, I haven't changed the question because I multiplied top and bottom by the same thing. Now, check this out. when I expand the top, I get sec squared x plus sec x tan x all over sec x plus tan x dx. Now, did you guys know? If I let this guy here be fx, then f dash x, the derivative of this guy, now the derivative of sec, what's the derivative? I'll do derivative of tan first, right? Derivative of tan is sec squared. Derivative of sec, for those that know, is sec tan. Huh. That is exactly what is now upstairs. Yeah. So the derivative of that function is upstairs. I can use this formula over here, right? So my answer is quite simply, if the derivative of a function is upstairs of a fraction, then my answer when I integrate is just ln of the function plus c. That's the answer, right? So you literally get it in like 2 steps. 1, 2, and you're there. If you know this hack, that's amazing, right? So it just works. Does it work for any other? No. Well, it works for sec. It works for cosec as well, where you times it by cosec plus cot. Exactly the same thing. How's that? Right? That makes this question so pleasant, because the reason why it's important for you to do it this way is because when I combine this, I'll do one more question, right? And that last question is going to be sec cubed. It is an extremely hard question because it deals with the by parts, it deals with special cases of by parts, it then utilizes this hack. It's amazing. So copy that down, all right? Method 1 takes about 10, 12 steps, takes about 10 minutes. Method 2 takes about a minute. Once I've done that longer because I had to explain to you where I got it from, but if you were to do this yourself, multiply something by the blue bracket, expand, boom, done, right? Now, always ask your teacher, if this question came up, can you use this way? Yeah, because sometimes they might force you in the question to say, because it says using the t substitution, right? Or using t result. So always ask your teacher. Guys, let's do one more question. This question has the lot. If it's like saying the last question was like my favorite ingredient in a pizza, pepperoni. Then this is like a pepperoni pizza, right? It's got pepperoni, my favorite, and other, right? I love my pizza analogies for this, right? So if I said to you, find sec cubed x dx, this is hard, man. This is hard. Remember, the approach for tackling trig, you got to ask yourself the question, if it's sec cubed, maybe I can decompose it and try to use some identities, right? So before I do this one here has a bit of recursion, right? Where you basically develop something that relies on itself. So I'm just going to let this guy here equal to I, just to make my calculations a bit easier. Guys, you're now faced with a question, right? How do I start, right? How do I start? So maybe if I sort of nudge you in the right direction, so sec cubed can be decomposed into sec times sec squared dx. If I asked you to apply by parts to this, now by parts, remember Lie8 says if there's log indices, log inverse algebra, trig, exponential, then that's the order you let u be, right? But what if they're both trig? What if one's sec and one's sec squared? If you go back to an earlier video of mine where I talk about by parts, this is key, right? This is subtle, and this is actually why Lie8 is in place. By the way, I think I mentioned in the video previously where some schools don't even teach Lie8. They just expect you to know what to let u be. That's bad, right? Lie8 is a good framework to start off. It's almost like the beginner's way of doing by parts. Once you're in expert level here, this is what you say to yourself. By parts is all about, not necessarily about the u, it's about the dv, because the dv is the integration part. It's always harder to find the expression to integrate. It's always easier. You can differentiate most functions. Very hard to integrate functions or most functions, right? So if I was to ever let a substitution fall by parts, right? If I say let u equal to and let dv equal to, always let dv be the one that you can integrate. That's why y8 is there. Because if you think about notion of y8, right? L is first for u, logs is first for u because it's very hard to integrate log. E is the last for y8 because if you put E as the dv, it's very easy to integrate E, right? So basically they reverse the order of difficulty to integrate to let you find U, yeah? While really what they're trying to do is get you to put the easier to integrate expressions into dv. Now, that's a long-winded way for me to say, what do you think I'm going to put into dv? Am I going to put sec or sec squared? Because they're both t in y8, right? Well, the simple answer is I'm going to put sec squared because it's easier to integrate. The integral of sec squared is 10. So this one here, my decision has been made for me. This guy is going to be dv, sorry, together with the dx. It's going to be dv. This guy is going to be u, right? So decision's made for me. This guy's going to be sec x. This guy is going to be sec squared x dx, right? It's been made for me. So when I do this, so differentiate u to get du. Now, I know that if I differentiate sec, I get sec 10. Yeah. If I integrate v, I get 10. Yeah, that's nice. Let's do by parts. So I know this guy, therefore, right, I, which is my sec cubed, equals to, by parts, be sec 10 uv minus the integral of sec times 10 squared. Nice. Now, you look at that and you're probably thinking to yourself, can I use u sub here? Can I let u be sec? But then the derivative of sec is sec 10, so that doesn't cancel. Can I let u be tan? Derivative of that is sec. You can't, right? You can't. So something else needs to be in there. So what I'm going to do for this one, I'm going to use sub in my identity for tan there, which is sec squared minus 1. See how I go. Right? See how I go. Let's use a little bit of trig substitution, right? Trig identities. Sec squared minus 1. Rainbows to expand out. Let's see where that takes me. Minus sec cubed. Ooh, sec cubed. Minus sec x. Now, check this out, guys. I know the whole purpose of me using I is that this integral of sec cubed is I. Yeah, so I'm just going to expand that by doing this. Sec x tan x minus I. Yeah, I'll put the red I over here, right? And then plus the integral sec x. There's my favorite question. There's my pepperoni, right? There's my favorite question. So this is what I'm going to do. I'm going to move this red I over here, collect them so I get 2i. I'm going to integrate sec x using the hack. And then because it's 2i, divide the 2 over and I get my final answer. So this is what you do, right? So 2 times a red I equals to sec tan, oops, sec x tan x plus, now I know using the hack, right? Well, let's just use the previous question. This guy's going, you times something by sine plus tan, sec plus tan, divide by sec plus tan, works out to be the ln formula. So let's just go there, right? Let's just go there. We know it's pepperoni, right? Yeah. And then divide everything by 2, boom, got it, right? So my final answer, right, is that integral of sec cubed, right, which is I, the red I, equals to a half sec x tan x plus ln sec x plus tan x plus c. How's that? That is a very hard question, but with a few hacks along the way, hopefully it's okay, right? That is a hard question, yeah? There you go. So guys, trigonometry with integration is meant to be hard. There's a lot of identities that you can use. There's T results now, there's this, and also next lesson, I'll show you some specific T substitutions that you need to do as well. That just makes this part, quite hard. I would consider this to be one of the hardest parts in probably the 4-unit syllabus, trig integration, but here it is, right? A few hacks. Hopefully that was okay. If you like that, give me a like, tell your friends. I'll see you guys next time.